In this video, I'm going to be answering the questions that I gave you about basic combinatorics. So let's get started. The first one is this one. What is a fundamental counting principle? What do we count? There are many cases in which the problems that you have involve having to choose from multiple options and having to arrange these options in different ways. So you have multiple scenarios. In many cases, you need to know them all. You need to actually write them down and choose from them, but in many others, you just need to know how many of them you have. And the problem is, how do you count them? That's the thing. You need to count these possible scenarios. So this is what this is all about. Um, the fundamental counting principle is just a rule of thumb, a way that we have to perform this operation, the counting. Imagine that I have this problem. I am in an ice cream shop and they offer 5 different flavors of ice cream, and I want a cone with 2 scoops, and I'm wondering how many different cones can I order with the condition that I have 2 scoops on them. So I could actually write down all the possible combinations between the flavors for 2 scoops, because it's just 5 flavors and it's just 2 scoops, but sometimes we have bigger numbers than that. Uh, you can try it on your own. Think of 5 flavors, list down all the possibilities and count them. But in here I'm going to show you how to use and what it is, the fundamental principle, the fundamental counting principle. So you have to choose 2 scoops of the flavor for the first scoop, and you have 5 different options. So for the first scoop, you can choose from 5. Any flavor of the 5 that they offer, you can choose it for the first one. Now, since they have to be different, in here I'm defining different in the sense that you cannot have 2 scoops of the same flavor. Okay, so for the second scoop, since you have already chosen one flavor for the first one, you have now only 4 possibilities. So these are the number of possibilities of possible elements, possible items that you can choose from for the 2 scoops that you are working with. And the fundamental counting principle states that all the possibilities come from multiplying the number of choices that we have. So we have 5 choices for the first scoop, 4 choices for the second one. So in total we have 5 times 4, 20 possible, 20 different ice cream cones with 2 scoops if we're choosing from 5 different flavors and not choosing 2 scoops of the same flavor. And this is it. The fundamental counting principle then is just multiply the options that you have and you're going to get all the possible scenarios. What is the meaning of this symbol, of the exclamation mark in math? And how is this operation called? And how do you perform this operation actually? Well, this symbol, the operation is called factorial. The symbol is also called factorial. And when you see it in front of a number, you say n factorial. 3 factorial, 4 factorial, 5 factorial, etc. The definition is this one, which is somewhat, well, not as clear maybe for some of you, but it's really easy to get once you see an example. Let's see this one. 4 factorial, and the operation is just a multiplication of all the numbers starting from 1 and leading up to the number before the factorial symbol, to the number before the exclamation mark. So in this case, 4 factorial is just multiplication of the numbers 1, 2, 3, and 4, all of them. This is a convention that the mathematicians use to actually put the biggest number first and then kind of go down. But it's just a multiplication of all the numbers up to that number. So 10 factorial will be the multiplication of all the natural numbers leading up to 10. So it's going to be 1, 2, 3, 4, 5, all of them up to 10. And here's the result. And if you notice this, 4 factorial is just 24, and 10 factorial is already more than 3 million. This operation, even if you are working with relatively small numbers, increases in value very, very fast. So you're going to be soon working with very big numbers with this operation. When you're counting, what does it mean that the order matters? Well, it just means what it says, that the order actually matter. And I think that you can understand it better with the ice cream example. Two popular flavors are vanilla and chocolate, and you could have chosen vanilla for your first scoop and chocolate for your second scoop and have this example over here. Or you could have chosen chocolate for the first one and vanilla for the second one and ended up with this, right? These two cones contain the same elements. They contain vanilla and chocolate, but they are arranged in different order, or maybe not. So that's the thing. If you say that these two cones are the same, that chocolate on top of vanilla or vanilla on top of chocolate are exactly the same cone, you're saying that the order doesn't matter. That the order of the scoops, the order in which the elements present in the arrangement does not matter. But if you say that these ones are in fact different, that they are not the same, then what you're saying is that the order does matter. That the string vanilla chocolate is different than chocolate vanilla because the order does matter. One comes first and then the other, and that's a different arrangement. So it all has to do with arrangements, and if in an arrangement you have the same elements but in different order, if you actually take them as different arrangements or not. What is a permutation, combination, and how do we count them? Well, permutation is just an arrangement in which the order matters. Combination is an arrangement in which the order doesn't matter. And I put this at the end because in here we're going to include all the other elements, because the mathematical formulas for these things includes the factorial symbol. And this is how we write it. We use the P for permutations, the C for combinations, N and R have the same meaning here and here. And N is just the total number of elements that could be arranged, which comes down to the options, the choices that you have. And the R is the number of elements that actually are arranged. Let's go back to the ice cream example again. So the same question, 5 different flavors. I want a cone with 2 scoops. How many of them can I order? And we had said from the fundamental counting principle that is just 5 times 4. 5 options for the first scoop, 4 options for the second one, 20 in total. If the order, but now that we know permutations, combinations, we can actually analyze this problem better. If the order does matter, which is to say that chocolate vanilla is not the same as vanilla chocolate, for instance, then since the order does matter, what you have is a permutation. And we will write it like this: a permutation, 5 permutation of 2, or the permutation of 5 elements taking 2 at a time. That's how you say it. But the thing is that you recognize that it's a permutation because the order does matter. You know that you have 5 different options in total because you have 5 different flavors, but you want only 2 scoops, so you're only taking 2 items at a time. And then just have to follow the formula. 5 factorial over 5 minus 2 factorial. That's this multiplication over 3 factorial, which in turn is this, which gives you this. This is the same as the result that we obtained with the fundamental counting principle, because the fundamental counting principle sometimes gets all the possible options, which means that the order does matter. That something like this, chocolate vanilla and vanilla chocolate, are counted as different options. What happens if the order doesn't matter? If this chocolate vanilla is the same as vanilla chocolate, for instance, well, then you have a combination. The order doesn't matter, combination. And you would have the same. 5 combinations of 2, or a combination of 5 elements taking 2 at a time. Again, the 5 because you have 5 options to choose from, and the 2 because you're only putting these choices into 2 boxes. You're only taking 2 scoops. So just follow the formula again. 5 factorial over 2 factorial multiplying 5 minus 2 factorial. You get this, which in turn is this multiplication, and you get a 10 as you'd expect because you're actually counting twice as different options. One thing that for these scheme of combinations is the same. And that's it. This is how it works. Of course, it can get more complicated, but we'll see